Hi everyone to another lecture. This is the second lecture with Johanna in gauge linears in my models. Please go ahead.
So hello, thanks, good evening and good morning. Thanks to everyone who came back. Last time I didn't get a lot of questions and feedback. I don't want to force you to ask any questions, but I'd rather have complaints about being too fast or too slow or my handwriting being unreadable than no interaction at all. So please feel free to come forward and ask questions and interrupt me. I'm not really in a hurry with the presentation. Okay, that said, let's come back to the main messages from the last lectures. So we were talking obviously about gauge linear sigma models. And basically the only thing I did 2 days ago was to set up the most basic data of the theory, which is the field content, the symmetries, and the last thing we did was to study the classical vacuum structure of the theory. And the whole point and the connection to, for instance, Calabi-Yau spaces that I like working with is that the scalar fields of the GLSM at the vacuum, at the ground state of the theory, they are constrained to sit on a certain manifold. And if you choose your GLSM wisely, this manifold can be a Calabi-Yau or any other manifold that you are interested in studying. So what I wrote down here first is the scalar potential. So the potential that covers the interactions of the scalar fields of the theory. I only need to look at that in the classical discussion because the vacuum expectation values of all other fields like the gauge field and the fermions will be 0 at the vacuum. So the vacuum is completely specified by the zeros of the scalar potential. And we have two types of scalar fields, the phi fields, where the complex scalar fields from the chiral multiplets, they are holomorphically dependent on the world sheet, and the sigma fields, which are Lie algebra valued, they come up in the vector multiplet. And this is what we're going to talk about mostly today. So in my last lecture, I talked about one class of solutions, which is typically called the Higgs branch. And it's those solutions where all the sigma fields are 0. And if you look at the two lines of this U of sigma, the solutions are determined by these D-term and F-term equations, which have a special form that is basically fixed by how you define the theory. And you can solve them. And the solutions will depend on one of the parameters of the theory, which I introduced, which is this Fi parameter. So it's one of the coupling constants. It's a real parameter, and the solution to these D-term and F-term equations, which determine the Higgs branch, can change when we vary these couplings. And this is something very physical. Take, for instance, QCD or other examples. When you vary the coupling constants, the theory may go into different phases. And when I talk about phases of GLSMs, that's also what I mean. So we have solutions that we can formally write as take the vector space that our scalar phi fields take value in. Remember, the sigma fields are 0 at this point. Sometimes the equations may not have a solution, and we have to notify that. This specifies this so-called deleted set F psi. We have a gauge symmetry acting, so we will have to take the field configurations that are related by gauge transformations to be equivalent. That's what this quotient here means. And if we have a superpotential in the theory, we also have to solve the critical equations, the F-term equations, and intersect these two solutions, and that will be our result. So the main example that I will discuss throughout these lectures, also when we come to D-brain, is the standard example and probably the first one of the motivations I think that the GLSM was invented for, which is the quintic Calabi-Yau. This is a famous Calabi-Yau threefold, which also plays an important role in areas like mirror symmetry, topological string theory, and so on. So it's an interesting model to study. And what we found is, so the first thing we had is that this can be engineered by a U1 gauge theory. So basically the simplest gauge group that you can have, like electrodynamics. And we had one Fi parameter, and we found that if the Fi parameter was positive, the vacuum configuration was a Calabi-Yau manifold. And the coordinates that described sort of the Calabi-Yau corresponded to the complex scalar fields that we had in our GLSM. So the scalar fields become coordinates on the Calabi-Yau. So we call this the Calabi-Yau phase. And if you were to look at the classical effective theory around this vacuum, you would get a 2,2 supersymmetric nonlinear sigma model with Calabi-Yau target space, but I haven't really discussed this. So the point is now, we have a geometry, but it only appears in, let's say, 1/2 of our parameter space, namely when the Fi parameter is positive. So we can also ask from like the field theoretic perspective, what happens if we take this parameter to be negative? Because this is within the allowed range. So if we do that, we found that this is something that doesn't really look like a geometry. So the low energy effective theory is a model which is with 5 fields, x1 to x5 as before, but they now no longer live in a projective space. They live in a 5-dimensional complex space. It has a residual set 5 gauge symmetry on it, making this space an orbifold. And there is a superpotential. And this is what's called a Landau-Ginzburg model. And this does not immediately have this realization of a nonlinear sigma model with a geometric target. But nevertheless, it appears as a phase of a theory which has the Calabi-Yau at the other corner of the moduli space. So in a sense, this Landau-Ginzburg theory is also Calabi-Yau and captures information about the Calabi-Yau. And most of what I'm going to do in my last lecture tomorrow is to tell you how we can establish correspondences between what happens in the Calabi-Yau and what happens in the Landau-Ginzburg model. And this is also where a lot of the non-trivial mathematics is hiding. Okay, but that's for tomorrow. So today I want to do 2 to 3 things, depending on how fast I'm going. The first thing I want to do is I want to give you another example of a GLSM which has 2 phases. So why am I doing that? Well, the quintic is nice and fine, and it's the most interesting example, or the first example to go to in many respects, but it's also been around for a while, so that already was in Witten's paper in 1993. So one can generalize this example in many ways. So one thing you could do, and people have done, is to look at further abelian GLSMs, which just have more than U1 gauge group. So the fields are charged in more than just one U1. And you can write down literally millions of models that are consistent and lead to Calabi-Yaus. And they lead to those Calabi-Yaus which are complete intersections in generalizations of projective space, which is called a toric geometry. So if you look into the lecture notes that Daniel kindly uploaded onto the website, you will see there is an exercise that covers a model with 2 U1s. And that has actually a lot more content, but with what I've told you so far, you should be able to figure this out yourself. And if you can't, you can look into a very nice paper by Morrison and Plesser, where they discuss this example in detail. And this brings into the year 1994, which is still quite a long time ago. So if you want to make contact to present-day research, or the research that's been happening in the last 20 years rather than the last 30 years, people have been looking at GLSMs with non-abelian gauge groups. So what I want to start off with today is to give you, or to sketch for you, an example with a non-abelian gauge group. And this is still, there are many questions about GLSMs with non-abelian gauge groups. And pretty much the example I'm discussing is one of only a handful of examples that are known. So I think there's a lot to be discovered, and that's why I want to take a little bit of time to tell you just a little bit about these more complicated non-abelian GLSMs. And then after that, I will go back to the vacuum structure of the theory. And I will move away from the Higgs branch and look at solutions where these sigma fields are non-equals to 0. And this will be called the Coulomb branch, and we will actually see, in order to make sense of the Coulomb branch, we also have to look into quantum corrections. So the Coulomb branch will have a very different flavor, and well, at least a third, maybe even more of the lecture will be about discussing that. And then if there's time, I will start the discussion on D-branes, which then leads us to this, categorical mathematics hidden by the GLSM. All right, so let's dive right into it. The model I'm going to discuss is called the Rutland model, after a Norwegian mathematician who had found a pair of calabi-Yau's that were somewhat connected, but not very well connected, in the sense that they had some topological numbers were similar, but some other topological characteristics were very different. And that caught the interest of mathematicians. And it was Kentaro Hori and David Tong in 2006 who established a physics connection between these two calabi-Yau's as phases of GLSMs. And this Rutland model is still studied today, and I've been writing a paper on it for 10 years and it's still not out. This is sort of the go-to example for non-abelian GLSMs. It's like the non-abelian cousin of the quintic. So as you know, if you study particle physics, there's a huge difference between gauge theories which have an abelian gauge group like electrodynamics, which is integrable, and non-abelian gauge groups like QCD or weak interactions where you have a much richer structure. So when you study non-abelian GLSMs, you very quickly run into rather fundamental problems that are similar to the fundamental problems of solving QCD. So studying non-abelian GLSMs is a significant step that you'll have to take, and that really raises the level of difficulty. So that's why I also apologize that I will be giving an overview of this example, but try not to dwell on the details, because that would be a lecture series of its own, probably. All right, so last time I discussed the data of the GLSM. So we basically do the same thing. We write down the field content, we write down the symmetries, we write down the scalar potential and the D term and the F terms, and we try to solve them and we see what we get. So it's always the same procedure, just gets increasingly challenging. So let's start off with the gauge group. So we have G, and so as a particle physicist, you would like to do SU2 or something like that. But actually, if you want to study calabi-Yau's, as I do, we're taking a U2 gauge group. So this is maybe a little bit unusual compared to other people who study SQCDs. But I have a reason for that. And the reason for that is that I need an Fi parameter. And an SU2 model would not have an Fi parameter, and I couldn't really talk about phases of GLSMs. So the next thing we specify is our chiral fields. And so we have the chiral scalar fields. And there's plenty. So I used to call all of them phi, so I'll keep doing that. So for the quintic, we had one field that was special and had different charges, which we call a p field. We still have something that acts like the p field for the quintic, but I'm going to take 7 of these. And then we had the x fields, which then became the coordinates of the quintic in the calabi-Yau phase. And I'm also taking 7 of these, but I'm not going to take them to, they are still scalar fields, but they will transform into fundamental representation of the gauge group. So they will also have a gauge group index. So they will be doublets. So, and I'll say G is in U2. So this is a unitary 2x2 matrices, and that the fundamentals just means that Xi goes to GXi. So picture the XIAs as column vectors with 2 entries. All right, so here we already see a big complication. So we know that the physical fields in a particle physics theory, they transform in irreducible representations of the gauge group. So if you take a U1 gauge group, the irreducible representations are easily classified. You just need to specify the charges of the fields. If you have a gauge symmetry like U2 or SU2, SU3, you have many, many more representations. So there is a lot more freedom to choose which representations you take for your field content. So in particular, I already said I choose the fundamental representation, which I denote by a box, for my chiral doublets. And then my p fields, I want to be singlets, but I don't want them to transform trivially. So since we have a U2 gauge group, the determinant of this group element will not be 0. So there is something called a determinantal representation. This is something you do not have in SU2, for instance, because the determinant of the group element is 1. So it's isomorphic to the trivial representation. So I will choose the representations, my P fields, transforming as the inverse determinantal representation. So, well, that means that the PI go to that G, that G, which is not 1, to the -1 PI. That's what that means. And I was a bit sloppy about defining how many FI parameters we have for each group. But basically, because U2 has a Weil group, there is 1 FI parameter and not 2. And in that sense, the model is similar to the quintic. I don't want to go into details, but there is more to be said. So, and then we have this R symmetry. And I will choose my R charges in such a way that the fields always have R charge between 0 and 2, and I will parameterize the freedom I have here like that. It's not very relevant for the rest of the discussion. All right, so then we have the sigma fields. So the sigma fields are those that take values in the Lie algebra of the gauge group, because they are in the multiplet of the vector fields. And that means, because the rank of the gauge group is 2, we now have not 1, but 2 sigma fields. So that's already a bit of a complication. So I will also write them as a column vector, or like a transpose of a row vector. And that takes values in the Lie algebra and the complexified Lie algebra of the gauge group. So again, there is a bit of a confusion with the standard notation. G underscore C is the complexified Lie algebra versus the G up here is the group element. All right, another thing that we had is the superpotential. So I want to construct compact Calabi-Yau's. The superpotential is optional, but all my models will have one. So what I choose is something very complicated. So remember from last time, the superpotential has to be gauge invariant, and it has to have R charge too. So how do we write down something? So for the R charges, you already see it should be bilinear in the x's, and it should be linear in the p's. So how do we do this in a gauge invariant way? So if you've done string theory and you looked at you look at how the two-dimensional metric transforms, you will actually see that there's you can just take the determinant by antisymmetrizing doublets. So what we can do is we can take xia, and then we can take the Levi-Civita symbol, the epsilon tensor in 2 dimensions, xjb. You can, for instance, set I equals j, because this just labels the fields, and put down the terms in the epsilon tensor and see how each component transforms. And you will see that this combination transforms with the determinant of the group element. So if we multiply this with a P field, which transforms in the inverse determinantal representation, this whole thing will be gauge invariant. And then I have a lot of indices to sum over, and I have to have some coefficients. So I have some complex coefficients here. And then I have to sum over all of them, I, j, k, and we have 7 of each of them. So we can do that. And I was a bit bad with my space, so let me make more room. We also have the group indices, A and B from the beginning of the alphabet go from 1 to 2. So we also have to sum over that. And then we have the superpotential, and that is gauge invariant. And in view of what we're going to see, I'm going to write this. I'm going to contract the indices and call this xi, xj, summed over. And I will write this as sum over I and j equals 1 to 7. So this is just a rewriting in suppressing the group indices aij of p, xi, xj. And because the xi, xj bracket is antisymmetric in I and j, aij is an antisymmetric 7x7 matrix, linear in P. And that will play a role when we discuss the phases. So this is a gauge invariant superpotential with 7 fundamental fields, 7 determinantal fields, and and with these R charges. So it satisfies our conditions. So what we're going to do next is we're going to determine the phases. So the phases of the GLSM are given by solving the D-term and the F-term equations. So I need to write them down for you. And at least for me, who doesn't know group theory and representation theory very well, you have to find a moment map equation. And I wrote that down for the U1 case, and it's a little bit complicated in the non-abelian case, and it's always a challenge for me. But luckily, Hori and Tong understand it much better than I do, and they have done the work. So you can look that up in the paper and check what the D-term equation is. So the moment map is gives you a real equation that maps this field space or the group into the field space. So what we have to write down is we take X to be a 2x7 matrix. So I'm just organizing my entries like X11, X12, where the upper indices are the group indices, and so on and so forth, X21, X22, and so on until X71, X72. So it makes sense to write something like XX dagger, where dagger is the standard complex transpose, conjugate transpose, everything is complex fields, and this will give you a 2x2 matrix. It's 2 times 7 multiplied with 7 by 2 gives a 2x2 matrix. And then we have the contribution from the scalars, and the minus sign here really comes from the fact that this transforms in the inverse determinantal representation. So the weights of these representations will be -1, and these are the gauge charges. So if we do that, we have a sum I equals 1 to 7 modulus pi squared to make it real. And then we have to multiply this with the 2x2 identity matrix. So all of this is a 2x2 matrix of equations that we get. And on the right-hand side, we have the Fi parameter, and again, the identity matrix, 2x2. And I will not write down the F terms because it's a mess. So what you have to do is you have to take the superpotential and take derivative with respect to each and all of the fields. So this is a lot of equations, and it's just taking derivatives, so I'm not going to write this down explicitly. Okay, so let's go to the phases, and we only have one Fi parameter. So the discussion at first will be very, very similar to the quintic. We'll have to distinguish between positive zeta and negative zeta. And we will have to see if there are any loci in the configuration space of our fields where these equations cannot be solved. So I'm going to skip a few details here and mostly state the results. So in the zeta equals 0 phase, when zeta is positive, you immediately see that you cannot, the right-hand side is a positive number times the identity matrix. So it is okay to set the p's to 0, but the x's cannot be 0. And what is more, this matrix X has to have full rank so that you also get something of rank 2 on the left-hand side. So that means that any solution where the matrix X has rank less than 2 will not be a solution to the D-term equations. So we have a deleted set, which I called F zeta larger than 0, which is that the rank of X is less than 2. So we only have a solution if the rank of X is maximal, which in a 2x7 matrix is rank 2. And furthermore, we see that counting F-term equations and using certain genericity assumptions, which are also more complicated than for the quintic, we see that we are allowed to set all the p fields to 0, just like for the quintic. And the only F-terms equations that are left, remaining F-terms, are sum I j equals 1 to 7, not infinity, xij xi xj equals 0. This comes from the F term with the p derivatives, but there are no p fields left after taking the derivative. So these are 7 equations. K is a free index, goes from 1 to 7. This is pretty much all we need to determine the phase in the theta than larger than 0 phase. So it turns out, and this is actually probably not so standard not basic algebraic geometry, that these brackets xi, xj's, which from a physics perspective we would call actually W bosons, they turn out to be coordinates, so-called Plöcker coordinates in a Grassmannian. So a Grassmannian is a generalization of a projective space where you don't have families of lines, but you have families of planes of a certain dimension. So the way this is written is that the xi, xj, so this combination of our doublets, they live in a Grassmannian of 2 planes in a 7-dimensional space, which is called G27, and they have to satisfy this F-term equation, which I'm not writing down again. So this equation here. And my claim is that this is a Calabi-Yau threefold. So remember that I had a condition in Calabi-Yau GLSMs that the weights of the corresponding representations have to add up to 0, and then the claim is that this GLSM is related to a Calabi-Yau. So you can actually check that with these examples. If you know a bit of representation theory and you know the weights of a fundamental representation and the weights of a determinantal representation, and you add that up, you will actually see that they sum up to 0. So that all works out. I will not show you that what the Hodge numbers are, or that actually this weight condition is equivalent to saying that the first Chern class vanishes. But one thing I want to get right is at least the count of the dimensions. And one fact is, so for the threefold, is that the dimension of a Grassmannian of k planes in an n-dimensional space is k times n minus k. So there's lots of binomials hidden in Grassmannians. They're very nice. So if we have k equals 2 and n equals 7, we have 2 times 5 is 10. So dim G27 is 10. And then we intersect it with 7 equations. And it's a complete intersection. So 10 minus 7 is 3. So intersected with 7 equations. So it's a threefold. So that's good, and it's fairly straightforward generalizations to the example we had on the quintic. It's a little more complicated. You can also see from a physics perspective that the gauge symmetry in this phase will be completely broken. Basically, in the definition of the G27, you put in the full gauge equivalence condition that the vacuum itself will no longer have any gauge symmetry. So it's a weakly coupled phase. So let me just write that down as a comment. So now we can ask yourselves what happens when theta is less than 0. So this is where we discovered this weird Landau-Ginzburg phase, which was not geometric. So here it actually turns out to be more complicated. And I refer you to the paper by Horry and Tong to see what kind of physics discussion is necessary to do that. One thing that's easy to see is when theta is less than 0, we are no longer allowed to set the p fields to 0. So we get our deleted set. F theta less than 0 is P1 equals P7 equals 0. So that already, since the p's live in a complex 7-dimensional space, this is again the vanishing relation for a projective space. So we're suspecting that the p fields are living on a P6, 6-dimensional projective space. Another thing we can see from the way that the p fields so the p's are non-zero. So they will be sort of the coordinates of whatever we get. Another thing that we can see is that because the P fields transform in this determinantal representation, there will be a residual gauge symmetry. So the symmetry will fix the P fields when the determinant is 1. And that is the residual symmetry that our vacuum satisfies. It's the analog of the Z5 symmetry that we found on the quintic that gave us the orbifold. So here it turns out that G equals SU2, which is the subgroup of U2, which has determinant 1, is unbroken. So our low energy effective theory will also be something like a theory weakly interacting, like a theory of weak interactions, and SU2 gauge theory. And because we have a non-trivial continuous gauge symmetry left, this is often called a strongly coupled phase. And that's important for the physics because strongly coupled theories are very hard to come by, like QCD. So that's why it's actually not so easy to analyze this phase. So basically what you'll have to do is you'll have to take a good look at the superpotential again and realize that the P fields that now having a VEF are like a mass matrix for the X fields in the low energy effective theory. And that there is a sublocus of the theory where the theory has massless modes. And the massless modes are usually those that really govern the low energy physics. So we can actually find a low energy configuration with massless fields whenever the rank of the 7x7 matrix drops. And this will be the degrees of freedom of the theory that will be relevant at the very low energies. Hori and Tong go through a detailed discussion of a Born-Oppenheimer approximation to do this. So what we see is that there are massless fields when the rank of A of P drops. And a careful analysis actually shows, so this is like really more details than I have time to give, is showing that the phase that is for negative zeta values is again a geometry. So it's again a nonlinear sigma model on a Riemann surface with some target space being a geometry. And the geometry is now given by P1 to P7, living in complex 6-dimensional projective space, where the fact that it's a projective space comes from the fact that we have this particular deleted set. And we have to restrict the configurations to the locus of the theory where there are massless modes. And that's given by the rank of A of P, which would normally be 6 because it's an antisymmetric matrix. If you are generic enough, you cannot reach rank 2. So the only non-trivial rank less than 6 locus that we have is the rank 4 locus. So that basically means you have to compute all the 6x6 minors of this 7x7 matrix and set them to 0. And this is not a complete intersection. It's called a determinantal variety because you have to like set determinants to zeros to specify it. And counting of dimensions is possible and a little bit more difficult, but the upshot is it's also a Calabi-Yau threefold. So what happens here is that you have a GLSM and you have a complex one-dimensional moduli space. And this zeta parameter is basically the volume parameter of the Calabi-Yau. So when you go to a large volume phase of the GLSM, you get 1 Calabi-Yau, and then you would sort of shrink the volume to 0, and you get another geometry, which is something very weird. I mean, a Landau-Ginzburg model is sort of not a geometry, but here it's really, you make the Calabi-Yau small and it tunnels through something and it becomes a different Calabi-Yau. This also happens in abelian GLSMs, but it's a bit more spectacular in the non-abelian GLSMs, because this x theta larger than 0 and x theta less than 0, they are topologically distinct, and in a rather strong way. And the mathematicians say that they are not birational. So birationality basically means that you can make transitions by Calabi-Yau's by taking P1s inside a Calabi-Yau and making them shrink, and then blowing up another P1. So there is a notion of a blow up and a blow down, which is changes the topology of a Calabi-Yau. So it turns one Calabi-Yau into another, and this is called a flop transition. So in this case, these two Calabi-Yaus, they are not related by what's called a flop transition. And therefore, well, it's not really obvious that they are connected. They still have the same Euler number, they still have the same Hodge numbers, but the other topological invariants, like the second Chern class or the intersection numbers, they are quite different. And this is called the Pfaffian-Grassmannian correspondence. So I should say that this is also often called the Pfaffian varieties or Pfaffian Calabi-Yau. Again, Pfaffians are determinants, a Pfaffian-Grassmannian correspondence. And this is quite an exciting topic, and people are still doing research on that, and it has a lot of connections to mathematics. So for instance, in mathematics, this connects to something called homological projective duality. This is sort of the mathematical term to connect these Calabi-Yaus. So this is due to Kuznetsov. There is also, in the physics context, it turns out that there is some, because we have like non-abelian gauge theory, there is a non-abelian duality. Similar to what people call Siebeck duality in other theories. So it relates two different GLSMs with two different non-abelian gauge groups that have tend to encode the same physics, and it also interconnects with this homological projective duality. And this is due to Horry in 2011. And there's also interesting categorical equivalences that have been intensely studied for these models in mathematics and also in physics in the last 10 years or so. So this brings you very quickly to present-day research, and there are quite a lot of open questions with these non-abelian GLSMs. And as I said before, there is no real classification or ordering principle which non-abelian GLSMs bring interesting Calabi-Yaus, and what kind of highly non-trivial connections between different Calabi-Yaus that you can make. And I would say this is still, when you can contribute to, like, by constructing new examples or by understanding, conjecturing new dualities for mathematicians to prove, this is something that's really present-day research. So you can write papers about this if you find a new interesting non-abelian GLSM. And that's also why I wanted to present that. The categorical equivalences, I will go back to the quintic to discuss that, but that will be the main topic tomorrow. Okay, I think that's a good point to take a breather and maybe ask for like 30 seconds if there are any questions, or if you want to have any more details or clarifications. While I'm a bit more silent, I'm going to scroll upwards to the scalar potential again. So I'm not seeing any questions right now, so I'm just going to continue. And we're going now back to simpler stories again, and discuss other, it's usually not called phases, but other solutions to the classical vacuum equations and their quantum corrections. So I think I had some kind of labeling for sections. Let me just go back and see. So the quintic was 3. Let's make the Rutland example 4. And now we're going away from the examples again and into the model, into the structural questions about geosense. And the next thing I want to discuss is the Coulomb branch. So this is as opposed to the Higgs branch. So we're going to ask ourselves now, we're looking at configurations where all the sigma fields are non-zero. So it's like really the opposite extreme compared to what we call the Higgs branch, where all the sigma fields are 0. And if you have a complicated theory, or you don't even have to go to a more complicated theory, you can just look at the two U1 squared example that is given as an exercise in the lecture notes. You will already see there is also a mixture between Coulomb and Higgs branches, but I will not discuss those. So all the sigma fields are non-zero. So sorry for the scrolling. Let's look at our scalar potential again. This is our main quantity to look at. So we have the sigma fields in each of the quadratic terms in the first line here. So and we have to get them to 0 individually. So we immediately see this, the sigma fields are in a Lie algebra. So in order to get the first term to 0, if we restrict to the maximally commuting subset of this Lie algebra, which is often called the maximal torus, and the sigmas commute, then the first term is gone. So this is the first way to solve this, but it doesn't really restrict the sigmas much. It just say that you have to look at the sublocus of the Lie algebra where the sigmas commute. And then for the others, there's always a mixing between sigma and phi fields. So what we would like to do in the generic case is we would like to set all the phi fields to 0. And this is also what we're going to do. But then we can look on and look at the D term and the F term equations. So if all the phi fields are 0, the superpotential, and by making, we always have to exclude linear terms in the superpotential. So they are at least quadratic. So that means that the F terms will be gone because all the phi fields are gone. And the left-hand side of the moment map equation will also be gone. And the only solution to the D-term equation will be theta equals 0. So that's only one point in the moduli space. And I had it in the picture for the quintic here. At theta equals 0, we still have to do some discussion. I had excluded this point before. And we see it's completely different because all the fields that determine the phases are now set to 0 in the vacuum. And everything is dominated by the sigma fields. So let me do some writing. So all sigma fields are non-zero. We must have, how do I best write it? The sigma are in the, sorry, this was my notation for the Lie algebra of the maximally commuting subgroup. And it's complexified. So that means that the sigmas must commute. And this happens, so U equals 0 for all the phi fields is equal to 0 and at theta equals 0. So I'm oversimplifying a little bit here. When we have more than one theta, one has to be a little bit careful about the solutions. But for the level of the discussion today, this will be good enough. This is called the Coulomb branch. And this is just a classical vacuum. And what do we have about the sigma fields and what is its configuration space? So what we had before is that the phi fields, after we've solved the D-term and F-term equations, lived in some compact space, like a Calabi-Yau threefold, or they were complex variables, but there was a potential. And usually when you are in a compact space, your spectrum is like a discrete spectrum when you solve the equations of motion. Here on the Coulomb branch, this is actually not the case. So the sigma fields, they live in the Lie algebra of the maximal torus, but that's pretty much it. So they can take all kinds of values. They are not constrained by any potentials and interactions. And that really changes the physics, that really changes the spectrum. So basically what that means is that the classical vacuum is a non-compact space. But which is not bad, but it's physically very different. So for instance, if you try to quantize it, the quantum theory has non-normalizable, oh, that's a long word, next line. Wave functions. So this is, the flavor of the theory changes completely. And the question is, do we have to deal with that, or is there something more to it? And in contrast to what I've told you before, where everything was like, take the classical vacuum, turn on classical fluctuations, and look what the effective theory is at long energies. In this case, we really, to see the complete picture, we have to take into account quantum corrections. So we must take into account quantum effects. And what happens? So I will not give a derivation because I'm really bad at quantum physics. It happens when you do topological field theory, you don't never have to compute higher loop corrections and lots of supersymmetry. So this, I refer you either to Witten's original paper or in the reference in the lecture notes, there is the reference to this big 900-page mirror symmetry book with the many authors. There is actually a nice account of this in section 15.5 in the mirror symmetry book. See references. By the way, this book has a really very good and detailed account written on GLSMs, written by Kentaro Hori, and that's why it's really good. So what you have to do in principle, if you're good at quantum field theory, is that you have to compute one loop effects. So, and what happens is that one loop corrections generate an effective potential for the sigma fields. So we already know that a low energy physics is dominated by the sigma fields, but they seem to be free classically. But then if you turn on quantum effects, you actually see that they are constrained by a potential, and that again compactifies your configuration space. And I'm writing here one loop corrections, and the miracle of supersymmetry and looking at theories in low dimensions is that it's one loop exact. So there are no high loop corrections. There are some instanton corrections as well that you can also compute. And all this was actually done in the 1970s by Schwinger, who studied two-dimensional electrodynamics with matter. And basically it's this calculation by a calculation, I think also by Coleman from 1976 or something, which computes this potential for the first time. And I'm just writing down the result and only will introduce what I need. So effective potential, because we have to take into account quantum effects, and we look at the low energy effective theory with quantum corrections on the Coulomb branch. And that looks as follows. And this is really basic quantum field theory. So people who know quantum field theory can actually compute that. So what happens is that you have all kinds of coupling constants. So for instance, the gauge coupling E that also made an appearance in the classical potential, that will just get quantum corrected. And that's what I mean by E effective. And what more or less happens is that the other fields you have, namely the phi fields, they get massive. So you have to integrate them out. And all these corrections that are dependent on sigmas come from integrating out the massive fields. And then we'll have a T effective, about which I will have to say much more. So bear with me, plus 2 pi I n. And what is this P? So this P we had before, this is the weight lattice. So there's some periodicity to this of G. And I haven't told you what the T effective is. I just want to mention that this sort of form of the potential, which will turn out to be linear in the sigma fields, is what electrostatic interactions look like in a two-dimensional theory. And that's why it's called the Coulomb branch, because it's like a theory of electrostatics in 2 dimensions. So this hopefully explains the name a little bit. So I have to tell you what the T effective is. So the T effective, remember I had introduced the T, which was this complexified combination of the Fi and theta parameter. And by the quantum corrections, both the Fi parameter and the theta angle, they get sort of quantum corrected as well. So this is also something that happens in quantum field theory. Your couplings get quantum corrections. And then you have randomization group flows and everything. So this is real physics. So the T effective stands for theta effective minus I theta effective. And I should highlight that this is the first time the theta angle makes an appearance. So in the classical analysis, the only time where our coupling parameters entered were in the D-term equation, and it was only the Fi parameter. And when you take into account the quantum corrections, you actually see that the theta angle also plays a role. This is, and I should say that this is something that mathematicians cannot fully appreciate. So if you look at mathematical definitions of the GLSM, and if you look at the literature of GRT quotients that Rachel Webb will probably tell you about in December, there's always a real parameter. But we physicists know that you have to complexify it. And this theta angle will be very, very important for the remaining lectures. So this is the point where it comes in. And it's highly non-trivial. So how are theta effective and theta effective defined? So they are defined by a critical locus of a function, which is called the effective potential of the Coulomb branch. So this comes out of the one-loop correction that I'm not going to show, that you can find in the mirror symmetry book or Witten's original paper, or in papers from the 60s and 70s where people knew how to do quantum field theory. And I'm just stating the result, and the point is that the result is completely determined by the data that I've given you when I specified the GLSM. So basically field content and gauge charges. That's all you need to know to write down what this effective potential is. So this is minus, and then I had this, it was maybe overlooked because I only briefly mentioned this. I had the pairing between the Lie algebra and its dual. So basically that stands for sum over A, TA, sigma A. Remember that the sigma A's are Lie algebra valued, so they can be expanded in terms of generators of the Lie algebras. And so are the T's. The T's are valued in the dual Lie algebra. And again, the T's here are, so at first, sorry for writing T's like that. And the T's here are just theta minus I theta. So this is the full T and not just the Fi parameter. And then from integrating out the fields that are massive, which will be our chiral fields, we get additional contribution. So we have a term I equals 1 to the dimension of the vector space the chirals take values in. And you take the gauge charges of each chiral and you pair it with the sigma fields. And then typically after you do some regularization and all the magic in quantum field theory, in one-loop corrections, you tend to get logarithms. And you get them here, and there's a shift by -1, which was overlooked in the earlier references, but we now know it's there. And then if you have a non-abelian GLSM, you'll have a shift that depends on the positive roots, alpha paired with sigma. So alpha are the positive roots of G. So you'll also have to find those. Let me just see. Yeah, so Daniel has just been asking about a 5-minute break. I think that's a very good idea. Can I just finish the discussion on the Coulomb branch and then we can take a break? Okay, I also don't mind having a break.
Sure.
Okay, good. So yeah, these are the positive roots of G. So for instance, e.g. for G equals U2, the root lattice is actually the same for SU2. The alpha sigma would be given by sigma 1 minus sigma 2. So alpha is basically a row vector 1 minus 1, and sigma, as we had, is a column vector. And if we have an abelian gauge group, this last term will not be there. The point is here, if you know the field content, if you know how many sigma fields you have, if you know the gauge charges of your chiral fields, you can write this down explicitly. So that means, and then up here, this T effective that I computed is basically take the real part and you get the theta effective and take the imaginary part and get the theta effective. And then you insert that into this potential and look for its minimum. And there will be some periodicity to it because the theta angle is periodic and it's free. And then you always have to shift in such a way that this U is minimal. And that's how this is to be understood. So I'm trying to find a good point for a break. So let me just state that if we take into account these quantum corrections, so on the Coulomb branch, we will see that we only have a Coulomb branch if the potential, if this new effective potential is flat, because everywhere else the Coulomb branch is lifted, because the Coulomb branch wants to be sort of situated at a minimum of this potential. So what we have is that the Coulomb branch only arises at U effective equals, I'm writing equivalent to 0 because we have this 2 pi periodicity. So, and maybe this is a good point to take a break. Exercise. Let's do this for the quintic. And I'll just take this general formula here and specialize for the quintic. So I'll give you a little bit more than it's in lecture notes. W tilde effective of sigma is, in this case, we only have one Fi parameter and one sigma field. So this angle brackets just is the product. So we have minus T times sigma. So then we have to go through each of our chiral scalar fields and take the charges and pair with sigma. So for the P field, we'll have a minus, and then the charge of the P field is minus P. And we multiply that with sigma. This is the first term up there. I should scroll down a little. And then we have log of the same thing, which is minus 5 sigma, minus 1. And then we have 5 X fields, which have each the same contribution because they have the same charge. So we'll have minus 5 times from the multiplicity of having 5 X fields. They all have charge 1. So it's 1 times sigma. And then log sigma minus 1. And that's it. U1 is one-dimensional. It doesn't have any roots, so we can forget about this I pi term. And that's it. So I'm going to take the 5-minute break now, and I'll give you 5 minutes to compute the sigma derivative of this. Set it to 0. Maybe take this equation, exponentiate it, and express e to the t in terms of whatever you get. and the solution will come in 5 minutes. So I think that's a good time to take a break. And of course, to ask questions.
Okay, great. Let me pause.
Okay, I don't dare ask. Has anyone tried to compute the critical locus of this effective potential? You can all say no if you want, or say nothing, then I'll just give you the solution. Or you can give a result if you want. Okay, silence in the chat, but I will just, so you just take the sigma derivative and you try to solve these equations. And what you should find is the following. So there is a Coulomb branch. And you can actually tease the complex parameter we have now, and it's good to express that in terms of e to the t, which is really the complex volume in the Kähler moduli space, if you think about Calabi-Yau's, and it's not, well, it's almost obvious if you take the derivative, but what actually happens, and this is very, very specific to the Calabi-Yau case, is that the sigma dependence totally cancels out. So what you actually find is that it's not a function of sigma, as you would expect. It's actually, because we only have one parameter, it's a number. And it happens to be -1 over 3,125, which is a number that people who know the quintic and who know mirror symmetry know very well. So that basically means, if you write that up, it means just that theta is 5 log 5. And theta, because of the minus sign here, e to the I pi is -1, theta has to be pi, and then mod 2 pi. And this is this mod weight lattice that I had before. Sorry, mod 2 pi. So this changes a lot, and this gives a lot of information. And I should also say that the mathematicians, they don't know how to do this calculation. And I think physics, despite mathematicians knowing lots of GLSMs and also knowing more about GLSMs than physicists in some respects, I think this is still very much in physics and not so much in mathematics, this calculation I just showed you. So yeah, I should say that the sigma dependence, as I just said, drops out. And so this is Calabi-Yau only. And I'll have some comments in a few minutes for the non-Calabi-Yau case. And we now have like now we have all values of theta. And theta equals 0 was something special in the classical, but by this quantum effect, it got shifted to 5 log 5. And something happened. So we now have the full stringy Kähler moduli space. Of the quintic. And it's the picture that we had before. And I should let me maybe repeat and distinguish between classical and quantum. Quantum meaning taking into account these loop corrections. So at the Higgs branch, we still have Calabi-Yau and Landau-Ginzburg, or Calabi-Yau or Pfaffian and Grassmannian, or whatever GLSM you have. And you still have that here. It's still true in the quantum world. So the low energy effective theories don't change. But classically, we've seen that at theta equals 0 and any theta, we have a Coulomb branch. That was the classical discussion before I went into the loop corrections. So we actually have like a solid boundary where the theory becomes singular. In a sense that we have like this non-compact directions at field space, that suddenly the phi fields have to go away and have to be replaced by the sigma fields in the low energy configuration. So we would have a barrier between Calabi-Yau and Landau-Ginzburg, or Pfaffian and Grassmannian. So now at the quantum level, we actually see that the classical value of theta gets shifted to theta equals 5 log 5, which is something like 7 or I don't know. And we only have mod 2 pi, a point, instead of a line. And that means, actually before the recording started again, Daniel asked these questions, is the physics in the phases isolated, or can we interpolate between them? And because we only have one singularity, there is now the possibility of like pushing things between phases, because the phase boundary is at codimension 1 in the parameter space. So we can go past it. So the question, can we make connections between things in the Calabi-Yau world and things in the Landau-Ginzburg world, or things in the Grassmannian world and things in the Pfaffian world? That becomes a valid question. And that will be what I'm going to talk about basically in the rest of the lectures after I've made a few more comments. So let me also already say that we see that the theta angle is periodic and it's drawn in the cylinder, the periodicity is implicit. So it looks like it doesn't make sense, it doesn't make a difference if the theta angle is pi, or if the theta angle is 3 pi, 5 pi, 7 pi, 9 pi. But as we will see when I talk about D-branes, is that it actually does matter. So it actually makes sense to like look at the covering space and write and unwrap the cylinder and put the theta angle on the x-axis and the theta on the y-axis. And then you see that you have like minus pi and 3 pi. And everywhere you have this like singularity. And up there is Calabi-Yau, and down there is Landau-Ginzburg. And it's now a valid question to ask, you know, how do I get past the singularity to interpolate between Landau-Ginzburg and Calabi-Yau, which physically is very different? And does it make a difference if I go to the left or to the right of a singularity? And intuitively you would say yes, because if you put that back on the cylinder, it's like you have a something, and I haven't told you what the something could be, and you have a puncture or a singularity somewhere in a complex space. And if you go around the singularity once, there will be residues and all this kind of stuff. So you should expect something to change depending on which path you choose. And this will be the topic tomorrow. And really, I should say, in the Calabi-Yau case, having this Coulomb branch and having this singularity in the modular space, this is responsible for so much of the richness that we see. So this is not to be underestimated. It's really deep to have this like singular point and to be able to interpolate between these phases. So before I go on and start actually discussing about what to transport, let me make a few further comments on the Coulomb branch. So the first comment is that I only gave you the quintic and the Pfaffian Grassmannian example, and they all have only one Fi parameter. So the first thing is there's an exercise for the Rutland model. We have 3 singular points, so 3 Coulomb branches. So what you'll have to do is you'll have to compute the effective potential for the Rutland model, which is an exercise in finding roots and weights of fundamental representations. And take into account that you have positive roots like here. Insert that, compute the critical locus, and you will find 5 different solutions. You will actually find more, but the one you have to mod out above our symmetry. And you will find, in the end, 3 different solutions, and that will be 3 points in the moduli space. And then the question of how to get from one phase to another becomes significantly more complicated. And understanding that is actually still work in progress. So that very quickly brings you from a 30-year-old result to an unpublished result. Okay, so I encourage you to look at this. It's a really, really simple and nice calculation, and you find the solution in the paper by Horry and Tong. Further comments, and I have to switch to somewhere else in my notes because this is something I added in compared to previous iterations of these lectures. So if you have so if you have more than one Fi theta parameter, so for example, there is an exercise, a concrete example in the lecture notes, U1 times U1, where you have two Fi parameters. There is also something called mixed branches. And these mixed branches, they are pesky to deal with, but they are also important because you also need them to really understand what happens at the boundary between phases. So the Coulomb branch is typically not enough. You also have to take into account, any U1 subgroup of your gauge group that may be unbroken on the Coulomb branch, and then some phi fields will be zero and some sigma fields will be non-zero and the other way around. So you'll have to work much harder to understand all these mixed branches, and only if you've done that, you will see the full quantum structure at the phase boundary. So this is sometimes hard work. So this is Calabi-Yau. For the non-Calabi-Yau case, so especially mathematicians are also interested in Fano manifold, and many physicists are not interested in Calabi-Yaus, but some general, QCD-like theories. So the non-Calabi-Yau case is really, really, really very different. So if you do the calculation for the quintic, you see that the sigma dependence drops out. And for every Calabi-Yau, you will have the sigma dependence will not completely drop out if you have higher rank gauge groups, but it will always reduce to some codimension 1 locus in the parameter space. So Calabi-Yauness makes a huge difference, and I just want to make a few statements on how a non-Calabi-Yau GLSM sort of behaves differently, because you really only see this on the Coulomb branch. So W effective in a Coulomb branch in non-Calabi-Yau case. So many things happen. So if you are if you take, for instance, the simplest non-Calabi-Yau example would be to take the quintic GLSM and remove the P field and remove the superpotential. And this will be the GLSM of just projective space, which is not a Calabi-Yau. So e.g. quintic example without P or W. So it's just 5 X fields with charge 1, which 5 times 1 is decidedly non-zero. So it's not a Calabi-Yau GLSM. And you try to do the same discussion, you will find there is no Landau-Ginzburg phase, but there is this Fano or projective space phase. And you can use the same potential for the Coulomb branch, but it will all be very differently. So for instance, I will always have this example in mind. So the sigma dependence does not drop out in a sigma W effective, I think I put a tilde here, is equal to 0. You can easily compute that. You get something like, I think sigma to the 4th is e to the minus t or something like this. So, or sigma to the 5, I'm sorry. So in general, in P4 GLSM. So more generally, the solutions to this, the Coulomb branch is defined basically by some polynomials or functions of the sigma fields. call them sigma A, modded out by some relations Fa of sigma A and the Fi parameters. So you get something like a polynomial ring. So this is like, and in mathematics, and this if you have a GLSM that corresponds to like a projective space or any other manifold, so that has a large volume phase, which is for instance P4, this encodes interesting mathematics again, and this is called the quantum cohomology ring. And if you look into the lecture notes, I cite this paper by Morrison and Plesser called Summing Up the Instantons, and you can do really a lot with this quantum cohomology ring, and you can actually also compute correlation functions in the GLSM using the information in this ring. But in the Calabi-Yau case, this sort of like all deflates and does something else, namely telling you where the singularities in the parameter space are. So this is very, very different, and I just wanted to drop the word quantum cohomology because many people know what that is. So I just wanted to, I didn't want to sweep that under the rug, but you don't see it in the Calabi-Yau case. Okay, there's also another thing that these kind of, so this is going to be a finite dimensional ring. It will be some polynomials, it will be finite dimensional. And in the category theoretic sense, there's also something mathematicians like in the context of homological mirror symmetry. This is something that's called a set of sheaves, which are called exceptional collections. This is just name dropping. To just in case people know these words, I want to write them down, and feel free to ignore this if you haven't heard of this. This appears very often in the mathematics literature on GLSMs and homological mirror symmetry. So I just wanted to say that in physics, this has something to do with the Coulomb branch. I should also say, and that's not obvious here, that the discussion of the phases is very different, because another thing that happens in the non-Calabi-Yau case is that zeta and theta in the Calabi-Yau case, they do not get renormalized. But in general, when we have a quantum field theory and we analyze the different energies, we get renormalized couplings. And the couplings will be scale dependent on the energy scale. And this does not happen in the Calabi-Yau case, basically because the moduli space is a true moduli space, and well, it's a CFT everywhere, and the couplings do not get renormalized. But actually, in the non-Calabi-Yau case, zeta and theta, if you do it at the quantum level, they get renormalized. And they will become energy dependent. So if we go back to the picture of the moduli space, because our couplings don't get renormalized, we can choose them however we want. But in the non-Calabi-Yau case, there will be a renormalization group flow, and that will push you towards a phase or away from a phase. And this is a phenomenon that doesn't appear on the Calabi-Yau case. And even though I will not talk about the non-Calabi-Yau case, I want to say that this is also why the physics of Calabi-Yau GLSMs is totally different, because your couplings don't get renormalized. You can freely access all the phases, and they're all at equal footing. There's no physics that pushes you towards a fixed point in a renormalization group flow. And that's the magic of Calabi-Yau GLSMs. They are really, really very different to non-Calabi-Yau GLSMs. So, okay, what we've seen now is that we can transport in the Calabi-Yau case, because we only have like a Coulomb branch at the codimension 1 locus in a moduli space, and we are free to choose our Fi and theta parameters the way we want. We can, so back to Calabi-Yau, I should say. So we can transport, and let me just say things, between phases. And whenever you have some kind of wall crossing phenomena, you want to know, what if I take something in the Calabi-Yau phase, what will I get out in the Landau-Ginzburg phase? And how does the singularity in the moduli space affect how I go around it, and what else do I get? All of this has interesting physics and mathematics hidden in it. So so what are these things? What can you picture in like putting in the Calabi-Yau context and getting out in the other context, or in the Grassmannian or in the Pfaffian? So the first thing you can transport is the geometry itself, and we have already discussed this. We have already seen that, like in one example, in one corner of the face you have one Calabi-Yau, and in another face you have another Calabi-Yau, or you have a Landau-Ginzburg model, or you have something totally weird called a hybrid model. So this is already something that you can see as an effect of transport, that you start off with a Calabi-Yau, you move in a moduli space, and suddenly it becomes a different Calabi-Yau, or it becomes a different model. So studying the phases themselves is already something useful. But we can do more, because to each of these phases we can attribute certain interesting things. We have a low energy effective theory there, and we can do all kinds of classical and quantum physics. And calculate this and ask, how do we transport from one thing to another? So things that people transport, both in mathematics and in physics, are, for instance, quantum states. So you have a theory, and so far it's like classical or semi-classical, but you can quantize this. And then you have like state spaces and Hilbert spaces of quantum states. You have creation and annihilation operators. So what do you do when you quantize a quantum field theory? It's not too magical. So you can ask, what are my quantum states? Of the theory in the phase. Or the phases. And in particular, as Daniel asked yesterday, there are there is always topological twists going on, and very often if you have a topological field theory, your state spaces are finite, and they have something to do with cohomology. So for instance, if you take a topological string theory of a Calabi-Yau, there are state spaces which are in one-to-one correspondence of certain state spaces of a IR conformal field theory, and you can just enumerate them, and they will be given by cohomology classes, or take values in cohomology classes of the Calabi-Yau. So this is, for instance, cohomologies. So for a Landau-Ginzburg model, you don't really have a cohomology of a manifold, but you have something similar that Waffer calls twisted sectors, and you can also count states there. And if you go to the very low energies, where you, in the Calabi-Yau case, always have a conformal field theory, so this would be CFT states. Keyword here is, if you've heard of this, chiral rings. So these are usually finite dimensional, and we like finite dimensional state spaces that take values in topological invariance. So that's a nice thing to have. And this you can transport. So you can ask, what is the quantum state spaces on the quintic? How is this relating to the quantum state space of a Landau-Ginzburg model? And this can be computed. And you can compute it on both sides. And there is math papers which prove. And then they say, oh, the Gen 1 cohomology associated to a Landau-Ginzburg model is equivalent to the even cohomology on the quintic. So these are the statements that you can get. And once you have states, you can insert them into correlation functions. You take the states you compute, and you compute them into some correlation functions, and you scatter those states. That's what you compute. That's also quantum theory. And if you are more mathematically inclined, these correlation functions, they have names. So for instance, in every Calabi-Yau or geometric phase, the correlation functions that you compute, they tend to be called Gromov-Witten invariants. I don't know how much time we will have tomorrow to talk about partition functions. Normally, Gromov-Witten invariants, or in the past, Gromov-Witten invariants could be computed via mirror symmetry. You take your Calabi-Yau, you find a mirror, you do the mirror symmetry magic, you apply the mirror map, and then you can extract chromophytin invariance out of something like a Yukawa coupling. So what's new is that you can actually compute this this chromophytin invariance directly from the GLSM, and as Daniel just commented that Giventhal himself will be a lectures, I hope I won't forget tomorrow to drop the words I function and J function, because this is exactly what you can compute with the GLSM. And if I don't have time tomorrow to tell this, I'm telling you today, all the things that you need for Giventhal's mirror symmetry are hidden in GLSM partition functions. So anyway, you also have something similar in Landau-Ginzburg models. You can also compute correlation functions there. And then the correlation functions would be called FJRW invariance of Fan, Chavez, Ruan, who actually worked that out based on, of course, work by Witten. So this is called FJRW invariance. Maybe you get Yongbin Ran or somebody else of his collaborators to give you a series of talks on that. Basically, in the physics terminology, this is our like certain topological correlation functions in Landau-Ginzburg models. And also these can be computed with GLSM partition functions. And I will not talk about those because I really want to talk about the categorical equivalences, and this is D-branes. And this is what the rest of the lectures is going to be about. So each of these topics is a 2-hour talk of its own. I'm really making a selection here. So I would like to refer you to the more recent literature, both in mathematics and physics, that is about computing correspondences between chromophytin invariance and FGRW invariance. Again, this is not mirror symmetry. This is just going in different limiting regions of the moduli space and basically computing the same thing, but very much in mirror symmetry, it's the physics and the mathematics that you sort of need to formulate these problems. It's totally different. A Landau-Ginzburg model is not a non-linear sigma model. There is no notion of a second cohomology class of a Landau-Ginzburg model. You have to translate this into something very, very different. So all of these correspondences are highly non-trivial. And the same thing is true for D-branes, and that's categories. So you see that if you have homological mirror symmetry, this is stated as an equivalence of categories. You say that the derived category of coherent sheaves on a Calabi-Yau is mirror to the Fukaya category of the mirror Calabi-Yau, whatever that means. And very similarly, but differently, different phases of GLSMs also, if you sort of enhance them by what physicists call D-branes, also can be, so the correspondence between phases can be augmented to the correspondence between certain categories associated to these phases. And if you're a physicist and you want to know how categories are coming in, you will have to talk about D-branes. And what I want to start off now is a discussion on what D-branes engaged linear sigma models are, how to characterize them, and then give you at least a flavor of what you need to do or what you need to understand if you want to take a D-brane in a Calabi-Yau and ask the question to which D-brane does it map to in the Landau-Ginzburg model, and what changes if I avoid the singularity in the Coulomb branch in the moduli space in different ways. So the rest of the talks will be very much focusing on this question, but I want to emphasize that all the other questions about correlation functions and so on, they are just as interesting. But since you're going to have Giventhal here anyway, who am I to give this discussion? All right. Good. So I think that is probably item number 6. Yes. New chapter. So again, this is a good point to interrupt me.
Sorry. In 2 weeks, there's going to be a lecture, also a mini course by Melissa Liu in Chromowitten. So I think it's
yes, it's covered. Yeah, you shouldn't ask me.
Yeah.
I only understand Gromov-Witten invariance from the early papers in the 90s by Witten and Dijkgraaf and Witten and Dijkgraaf, Verlinde. And if you want to understand Gromov-Witten theory as a physicist, homework for you before Melissa's talk, read old papers by Witten and Dijkgraaf from 1990. They are fantastic and they explain to you what Gromov-Witten invariants are in a physics term. All right, so yeah, D-branes. Good. So yeah, let's start again. So I have largely suppressed the fact that the GLSM is a gauge theory in 2 dimensions and that it lives on a worldsheet, and the worldsheet is a Riemann surface. It hasn't really played much of a role in our discussion so far what kind of Riemann surface this is, if it's homogeneous, if it has a boundary or not. Because the phases basically don't see this, they only see like this potential, and you compute the zeros of the potential, and you hope that your phi fields, they are scalars, so they will happily live on any Riemann surface. So it hasn't mattered to us really what the details of this Riemann surface are, and that's why I also didn't emphasize it. So if we have D-branes, D-branes are boundary conditions for open strings. So if you have D-branes, you have to think about what your worldsheet is and what you want to compute. So what we will do is we will put the GLSM on a worldsheet with boundary. And for now, in order this discussion, as I consistently will not introduce actions, this discussion will be qualitative. But what you should have in mind is the simplest possible case, and when you do the derivation that I'm not going to show, this is also what you're going to do. So you will assume that your Riemann surface is a strip, a flat strip. So sometimes it's useful to assume that it's a sphere or a cylinder or something, but for the sake of the discussion here, we will have done a Wick rotation, and we will have a real coordinate, which is the Wick rotated time coordinate, and then we will have an interval, which is the left and the right end of the strip, and that will be our boundary. So, so it's a strip and the boundary, well, it's very intuitive. So then a lot of things will change if your space-time has a boundary. When you take normally what you do to derive equations of motion, and that you get yourself started in the field theory, you compute the variation of the action, you compute the Euler-Lagrange equations, and that's it. But if you have a boundary, you have to worry about boundary terms, and you have to give boundary conditions to your fields. You have to say what kind of boundary, how the fields behave at a boundary, and that has to be consistent. And what is more, when you have supersymmetry, you also have to ask, how much supersymmetry do I have left? Because usually we want to have a little bit of supersymmetry left because that makes life easy and well organized, and that's good. So what we will do is we will not consider the most general boundary conditions, but we will consider boundary conditions which preserve the maximum amount of supersymmetry. So we have a 2,2 supersymmetry on the closed string worldsheet, so two supersymmetries to the left and 2 supersymmetries to the right. And for those people who've seen supersymmetry, the supersymmetry algebra closes on translations, and the presence of a boundary obviously breaks translation invariance in the direction perpendicular to the boundary, so you will never be able to preserve all the supersymmetry when you have a boundary. So the best you can do is to preserve half of the supersymmetry, and that's what we're going to do. So we consider branes, or boundary conditions, which is, I'll just say D-branes, that break half of the supersymmetry.
Are these Riemann manifolds that you are considering general genus or genus zero?
That's a good point. So for now, many of the statements I make will also be true at higher genus. But we will have to deal with fermionic degrees of freedom as well. And when you have like a spinner, it's a delicate question whether these spinners live on what kind of surface these spinners live. So in principle, I will have also higher genus worldsheets, but I will, if I were to talk about higher genus, which I will not, you should always have in mind that I've done a topological twist. And that's also something I should say once I'm finished writing this sentence, that all the D-branes I'm considering are actually D-branes that also exist in the corresponding topologically twisted theory. And if you go to higher genus, you should always also impose the topological twist, which turns your spinners into differential forms or scalars, and then things are fine again. So yeah, that's a very good question. But yeah, for what I say is certainly true for genus 0 and for the strip. And if you want to make sense on higher genus, you should also put a topological twist. And that will not, for the D-branes I'm going to discuss, the topological twist will not remove any D-branes. So the D-branes, in other words, the D-branes that I will consider are also topological D-branes. Okay, yeah, thanks for this question. Okay, so we want to break half of Susie. If you take, for instance, Witten's paper on mirror symmetry and topological field theory, and also, or if you look at Aspinwall's iconic lecture notes on D-branes and Calabi-Yau, you will see that in 2,2 theories, there are two options, inequivalent options to do this. And they lead to something called A-branes versus B-branes. That brings me back to Daniel's question. A-branes are also the branes that are visible to the topological A model, and B-branes are also branes that are visible to the topological B model. So it will always be compatible with the corresponding topological twists. So, and what you will get is 1,1 Susie, which is not 0,2 supersymmetry, which is related to the heterotic string, which also breaks out the supersymmetry and is related to interesting physics. And the guy who's sitting next to me is the expert on that. All right. So A-branes on Calabi-Yau are like objects of the Fukaya category, and they're notoriously hard. And as far as I know, A-branes in GLSMs are not fully understood. So there is a paper by Horry called Linear Models in Supersymmetric D-branes, which is already quite old, but still covers pretty much all that's known about A-branes. For B-branes, we know what we know now, and which I'm going to discuss, but A-branes are still largely unknown, let's say, and that's why I will, out of necessity and due to my ignorance, only talk about B-branes. And the transport of B-branes is really well understood, and also B-branes and GLSMs and phases are well understood. So we'll be safely living in not Fukaya categories in the discussion. So derived categories of coherent sheaves or something called matrix factorizations, which I want to introduce today and then continue tomorrow. And this will be our B-branes. So when I talk about D-branes in the GLSM, I only mean 1/2 of the nice D-branes that break half of the supersymmetry, and these are the B-type B-branes. All right, so this is my big disclaimer. So what you'll have to do now is you have to choose B-type boundary conditions that basically tell you which 1,1 subspace of the supersymmetry you want to preserve, and compute the variation of the action, and compute the boundary term and see what happens. So the procedure that I'm not showing, and I'm only going to sketch it, and then we'll get serious tomorrow, is compute B-type SUSY variation of the action. And, well, you will find boundary terms. So if you do that, the same thing, for instance, for like the fermionic string that you learn in lectures of string theory, if you do the superstring, you then look at the boundary terms and you cancel the boundary terms by imposing certain boundary conditions on your fields. So, and typically we must choose boundary conditions for our bulk fields. So all the fields I've introduced so far will now be called bulk fields because we also have boundaries. So for example, and there is nothing difficult or magic about this. If we take our chiral scalar fields, one boundary condition is, for instance, that they take constant values, and you would call that a Dirichlet boundary condition. And that's also where the name D-brane comes from. Or you could say that the derivative with respect to the normal derivative, I think, with respect to the phi i's of z on sigma has to be 0. So that sort of the string oscillates freely at the boundary. These are called Neumann boundary conditions. And then for the fermions, you have the choice of periodic and antiperiodic boundary conditions. So these are like standard things you do when you have theories, and you usually have Dirichlet or Neumann or something like that, and something for the fermion. So the problem for the GLSM and also for a Landau-Ginzburg model is that, so for GLSMs, Landau-Ginzburg, or more generally theories that have these holomorphic potentials, so theories with W of phi, this potential, this is not enough. Because you will not be able to cancel all boundary terms. And the reason for that is if you take the variation with respect to this B-type SUSY, which I haven't specified, but you can, for instance, find worked out in this mirror symmetry textbook, but I'm not doing any SUSY variations, of your GLSM action, you will find that there is a term which is something like the real part. You integrate over the boundary, the x0 coordinate is sort of the coordinate that's left. Epsilon bar, which is the SUSY parameter. Psi I, which are some fermions. And then you have dw d phi I. So the psi is the fermions you want to give periodic or antiperiodic boundary conditions, as you would usually do in a Rothschild theory. So basically the only way you could cancel this term is by having a constant superpotential. But we have already agreed that non-constant superpotentials are really interesting because we want to have, like, for instance, the quintic superpotential. And this is a problem. We don't know how to cancel this term just by choosing like boundary conditions for the phi and the fields and the fermions and everything else we have, and by choosing like boundary terms that depend on the phi and the psi fields. And this problem is due to Nick Warner, and is therefore called the Warner problem. And it was around since 1989 because it appeared in the Landau-Ginzburg Landau-Ginzburg models. And this has been a problem for a long time. And for Landau-Ginzburg models, so I should also say that W is constant, is too constraining. We don't want that. We want to be able to compute a quintic. So this Warner problem has been around for a long time, and it was solved for Landau-Ginzburg. By the first who do this were Kapustin and Lee in 2001. And then for the GLSM, and this is what I'm going to talk about, by Herbst, Horry, and Page in 2008. Sorry, the first one is in 2001. And they found a way to cancel these boundary terms, and they did this at a price, namely that you have to introduce additional new degrees of freedom that only live on the boundary and do not live and have no correspondent bulk field. So it's not a bulk field that takes values on the boundary, it's a new field. So we must introduce new boundary degrees of freedom for boundary fields. And this I will not do explicitly because it's very technical and very complicated. So the upshot is, and this is where I want to pick up tomorrow, that these extra boundary fields satisfy something that's called a matrix factorization conditions. So the extra or let's say extra degrees of freedom are matrix factorizations. So this is something that has been known since 1980 in the context of singularity theory. They were invented by Eisenbud for something that had nothing to do with deep brains, and then Kapustin and Lee, based on an idea by Kontsevich, could show that these matrix factorizations are useful in the context or are describing B-type deep brains in theories that have a 2,2 theories which have a potential. So just to tell you what I'm going to do more rigorously tomorrow, we will see that there are matrices, I call them Q, and they will depend on the chiral fields that we have before, such that they will have square matrices with polynomial entries in the phi i's. So the bulk fields still are playing a role, but the fact that we have matrices sort of encodes this new degrees of freedom that we have on the boundary. And the fermionicness I didn't really say that the new boundary fields and they are fermionic. The fermionicness will manifest itself in a certain grading. And matrix factorization means that I find any square matrix with polynomial entries and I square it. That's why it's called factorization. And that gives me back the superpotential times an identity matrix of a suitable size. So you can derive this condition from this recipe I gave above, compute the SUSY variation, and introduce additional degrees of freedom that only live on the boundary, that you add onto the action such that the combined bulk boundary action cancels this term. And that leads you to the matrix factorization condition. So I think this is a good point to stop. So what I'm going to do tomorrow is I will basically define, just like the GLSM data, I will define how to specify a B-type deep brain in a GLSM in more detail. And that will take me a while. I will give a few standard constructions. I will give examples for the quintic. And then I will talk about these categorical structures that appear and the deep brain transport. And basically what I will do is I will follow this wonderful paper by Herbstory and Page, which I suggest you look up on the archive. It has 260 pages, and I will not be able to do it justice, but I want to at least give you an idea how this works and to see how this deep brain transport can be implemented. All right, and I think I'll stop here. Thanks for listening.